So the latest little bit of internet crazy in rabbit hole terms that I've been down is, believe it or not, the flat earth rabbit hole. Question is often raised about, oh, I can't see the curve of the horizon. And you can see the curve of the horizon when you get up higher. When you go up in a balloon or a spacecraft, you can see the curve of the horizon. So the question comes up, how high do you have to go to see the curve of the horizon? And I saw a YouTube video that was trying to explain this, and I couldn't really understand the geometry, so I wanted to, just as an intellectual exercise, see if I could figure out myself what the whole the geometry of such a thing would go on, would be about. So in order to do this, I've built myself a model of the Earth. Well, it's not much, didn't do much building really. It's a basketball, and it has a wire man sitting on it. So this bit here represents a person standing on the surface of this spherical Earth. So yeah, that's the line of sight to the horizon. So if he's looking down that bit of black wire there, that's the line of sight to the horizon. And I've got another line of sight to the horizon. Over this side, there's a line of sight to the horizon there. You can imagine the guy sitting there, standing on the Earth's surface, and if he looks off in that direction, he can see the horizon where his finger is. And then if he turns 90 degrees, he can look off to the horizon 90 degrees this way, where this other finger is here. And if you look straight ahead, you know, he would expect to see the curve of the horizon going over like that. And the question is, how much of that curve can you see? How big is that curve at any given height? The shape of the little wire thing looks like this. It's kind of triangular, but it's got this arch, and this is it's the height of this arch that is the question. How high is that arch for a given height, observation height on the sphere? So yeah, figuring out the maths of that, and triangle with this side here. This is the distance to the horizon for a person who's that high. So, and I've just decided we're going to assume that the person's looking out one way and then looking out the other direction 90 degrees, so their field of view is 90 degrees. In other words, this angle here is 90 degrees. So you've got a right angle triangle with two sides that are the distance to the horizon. Now we've got some maths that can calculate the different distance to the horizon, and therefore, because this is actually an isosceles triangle, and if you know the distance on these two sides, you can tell the distance across the bottom there. And once you know the distance between those 2 points, and you know the shape of this circle, because this circle is the surface of the Earth, so you know the radius of this circle because you know the radius of the Earth, you can actually figure out how high that space there is using geometry, and that can tell you how high the arch, the dip, or the bulge should be. So we need to know the distance to the horizon, and you can figure that out using simple geometry and Pythagoras' theorem. So if you have a diagram like this, which has got a person that's h high, standing on the surfaces of a sphere and then looking off to the horizon along a line of distance d, so that's a line that's tangential to the surface of the Earth, with a radius of the Earth of RE, then you have geometry that is a right angle triangle, and you can set up an equation describing that geometry in Pythagoras' theorem, and you can solve that equation for known heights and known radiuses of Earth. And if you do that for a height of person of 2 meters, then the horizon is about 5.1 kilometers away. Okay, so now we know the distance to the horizon is 5.1 kilometers, and so we need to figure out what the other distance is on this triangle, the distance across the bottom of the arch, and we can do that also by Pythagoras' theorem. So that triangle that's in there, we know we've got a right angle at its apex, so there's actually two isosceles triangles there, 45 degrees angles in them, and the base is 5.1 kilometers, so we can figure out the unknown distance there, A, from Pythagoras' theorem, and it is 3.57 kilometers. So we know the distance across the base of the arch is 3.57 plus 3.57. So from that we can now figure out the geometry of the bulge. So now we look at the geometry of the arch, the bulge. So this is a diagram of that looking side on, and we've got the height of the bulge is unknown as h, and the base of the bulge, as we previously determined, is two lots of 3.57 or 3.6 kilometers wide. So that's marked on the diagram here, and then we've got the radius of the Earth. So we have a triangle there, a right angle triangle, with a side of 3.6 kilometers, another side of, which is the radius of the Earth, and another side radius of Earth minus h. And you can use Pythagoras' theorem to construct a relationship there, and it actually turns out to be a quadratic equation as shown here, which you can solve for h, the height of the bulge. So yeah, the height of the bulge is about 1 meter high at 3.6 kilometers distance, and so the question is, would you really be able to see that much, that small of a bulge at that distance? Well, the way to really answer that question is to figure out what the angle that sort of height would subtend at the eye, because that's the way you sort of determine the resolution of the eye, by measuring what sort of angle difference that sort of height would have at the eye, and you can do that again using geometry. We've got a 1 meter height difference at 3.6 kilometers away, and the question we're going to ask is, what is this angle here? This angle that it's this 1 meter height at 3.6 kilometers, what angle that subtends at the eye? So you can, this diagram is equivalent if you divide this triangle into two right angle triangles with an angle of alpha on 2 and a height of 0.5 meters. You can use trigonometry to figure out that 0.00014 radians, alpha on 2. So you figure out that alpha is actually 0.016 degrees. So the bulge would only subtend an angle of
0.016 degrees, and it's generally recognised that the eye's sort of resolution is actually 0.02 degrees. So this is less than the resolution that the eye can detect. And so yes, at a height of 2 meters, you cannot detect the bulge of the horizon. So you can't really detect the bulge of the horizon if you're just standing 2 meters off the surface of the Earth. That then raises the question about, when can you see the bulge of the horizon? So, I mean, I've actually got this stuff stuck in a spreadsheet, so I can solve this for any observer height. So let's see what the angle of, how high the bulge is and what angle that might subtend at the eye for 120,000 feet, shall we? So 110,000 feet, shall we? 110,000 feet, I figured out, is about 33,000 meters. So if we put 33,000 meters in here, yeah, that's 110,000 feet, or 33 kilometers high. That gives me a distance to the horizon of 650 kilometers, so you can see a lot further. And the height of the arch, the height of the bulge, that, when you're observing at that height, so out in space a fair way, 20 miles I think out in space, yeah, the height of the arch is 16 kilometers high, and the angle that subtends at the eye is a whole 2 degrees. So at that height, if you've got a field of view of 90 degrees, then you expect the height of the bulge to be, to be 2 degrees at your eye. So yeah, at 20 miles high, you'd expect to see a slight curve on the Earth's surface, which is exactly what you do see if you go up that high. And you don't even have to take NASA's word for it. You can even find guys on the internet that are sent up their own amateur rockets to about that height and look at their video footage, like this screenshot here from this guy's YouTube video, where you can clearly see the curvature of the Earth at that 120,000 feet height.